We're going to talk now about our shortcut for finding horizontal asymptotes on the graphs of rational functions. So this is called horizontal asymptotes and end behavior of rational functions, because really a horizontal asymptote is just telling us about the end behavior of the function. I'm going to give you the rule first, and then I'm going to talk a little bit about where the rule comes from. So other than you have to know the rule and how to apply it, but the rest of the video is optional. So here we go. Let f of x equal p of x over q of x be a rational function where p and q are polynomials. If the degree of p equals the degree of q, then f has a horizontal asymptote at y equals the lead coefficient of p over the lead coefficient of q. Number two, if the degree of p is less than the degree of q, then f has a horizontal asymptote at y equals 0, which is the equation of the x-axis. The x-axis is a horizontal asymptote. If the degree of p is greater than the degree of q, then there is no horizontal asymptote. Now we've seen a couple examples so far, right, of graphs. We graphed our 1 over x. That's a case where the degree of the numerator is less than the degree of the denominator. So that's like a number 2 situation. And that's a graph where the x-axis, or y equals 0, is a horizontal asymptote. We also did one example so far. We looked at 2x plus 1 over x minus 1. That's an example of the situation in number 1 where the degree of the numerator and denominator are the same. Here they're both degree 1. And so we can just take the coefficient of x, 2, over the coefficient of x in the denominator, 1. 2 over 1 is 2. So the line y equals 2 is a horizontal asymptote to that graph. And we're going to apply this in more examples. But before we do a bunch of examples, where does the rule come from? Why does it work? So what follows is an optional discussion of the reasoning that justifies the rule. So if you want to skip this, if you're not curious about where it comes from, you can. But for those who are curious and want to know why the rule comes out the way it does, try to follow this little explanation right now. So we're going to look at some examples, and first example is a pretty complicated rational function. F of x equals 3x squared plus 2x minus 4 over 4x squared minus x plus 10. So notice that the degree of p, the numerator, equals the degree of q, the denominator. They're both of degree 2. So the rule tells us that we can find the horizontal asymptote by taking the lead coefficient of numerator and denominator, so 3 above, 4 below, and write y equals 3/4. That's going to be a horizontal asymptote to the graph of f. And then the question is, well, why does this work? Why can we use this little trick? So let's go ahead and look. I'm going to work with some numbers here. We're actually going to look at what happens as x approaches infinity and gets very, very large. And so I'm going to plug in some numbers. So for instance, first I plug in x equals 100 and calculate f of 100. Now, before we start simplifying this, notice that because we're squaring, when we square 100, we get a much larger number than when we just have 100 by itself or a constant term. So these terms at the beginning, this portion of the rational function expression, this portion dominates. And the remaining portion, I'm just going to kind of put a dotted line around this, of the fraction, is relatively insignificant. Helps me a little bit to think of money, if these were dollar amounts. You know, if I get $30,000, and then I get $200 more. Well, that 200 doesn't make that big of a difference if I already have $30,000, even though $200 by itself sounds like a lot, right? Same thing, 40,000 is a lot, but if it turns out I have to give back 100, well, if I got 40,000, it's not that painful to give back $100. So it's all a relative kind of thing. Now, this fraction, 30,000 over 40,000, notice that it just reduces to 3/4. There's that 3/4 that we've been talking about. And I got a calculator value, but the calculator value isn't so interesting here. This is 0.7566 approximately. Now, if I plug in a larger value of x, what I want you to see is now these early terms, these first terms, leading terms, dominate even more. If I plug in 1,000, this is like, in the one numerator is 3 million plus 2,000 minus 4. So in terms of dollars, 3 million's a lot of dollars. And it's all relative, right? Because now 2,000 doesn't sound like so much if you're dealing with dollars in the millions, right? So it's still true, even though these terms behind are larger now, some of them are larger, the first terms still dominate. And I'll say relatively insignificant, the terms that follow. So plugging in actual numbers and leaving the terms separate here help us see the domination by these terms of leading terms, these terms of highest degree, highest power of x. And as x gets larger, the one observation to make is they dominate even more and more. So here we got, what is that? 300 million over 400 million dominating. And even though, again, 20,000 sounds like a lot of money, 10,000 sounds like a lot of money, but if I have $300 million in my pocket, 20,000 more really isn't that big of a difference. Or if I have $400 million in my pocket, having to give back 10,000 doesn't really make that big of a difference. So this fraction dominates, and when you reduce it, this ratio is just, notice, 3/4, 3/4, 3/4. And overall, we're just going to get closer and closer to 3/4 because the domination becomes greater as x becomes greater, and the insignificant terms become more insignificant as x becomes greater. Let's see, I got 0.7507. 0.7507 here. I was just going to give you these decimals, but the decimals are not nearly so interesting as just looking at this domination of certain terms. And 0.75, this is going to be 0.1 rounded off, just. All right, now that's as x approaches infinity. What about as x approaches minus infinity? And so the question is this situation different, or is it similar? And as x approaches minus infinity for the same function, so if I plug in negative 100, again we got the dominating terms. Again we got the dominating terms. This is when I plug in negative 1,000. Basically we see we're getting the same ratio whether we go to positive infinity or negative infinity. So even as x approaches negative infinity, the function values approach 3/4. The actual decimals that I get here are a little bit different. At negative 100 it's about 0.743. And at negative 1,000, 0.7493. So the difference is, here these are all a little bit less than 3/4, But as x becomes more and more negative, we're certainly going to get closer and closer to 3/4 the same value is approached. So that's a situation when the degree of the numerator equals the degree of the denominator. Let's look at example 2 now. So this is a different polynomial now. 5x squared plus x minus 30 over 2x cubed plus x squared plus 1. And here the degree of p is less than the degree of q. So the rule tells us that when the degree of the numerator is less than the degree of the denominator, y equals 0, or the x-axis, is a horizontal asymptote. So let's ask why. Let's look at plugging in numbers again, just like we did before. Here again, in this situation, these lead terms dominate. The contribution from the remaining terms is relatively insignificant. Now here I want to look at what this fraction reduces to. I can cancel a whole bunch of zeros, right? 4 zeros. I think this looks like 5/200ths as a fraction if I just look at those lead terms. When x is 1,000, again, these lead terms dominate. Now, I don't get the same ratio like in the previous example. I'm actually getting 5/2,000, I think, right? 5/2,000. So notice this dominating ratio is changing. It's not the same. And I even wrote out 10,000. What is it? That's like 500 million over, what is this, millions, but 2 trillion, I think that is below. So notice, when you have $2 trillion, believe it or not, I have a hard time believing this, but $100 million is relatively insignificant, right? And that it's really on that same scale, that's true. But here, if we look at that ratio in front, I think I'm going to have 5/6, 7, 8, 2, 3, 4, 20,000 at that point. So the initial terms dominate again, but what's happening is the ratio, or the fraction, this fraction, is getting smaller and smaller. This fraction is approaching 0 in the sense that we'll get closer and closer to 0 as we take larger and larger values of x. So that's the difference here. When the degree of the denominator is greater, the force of that, in my mind, the denominator is growing much faster than the numerator, so it's kind of overtaking the thing, and it's dragging the whole fraction to 0, right? So what happens as x approaches minus infinity in this situation? If we look at the dominating terms, I think the only difference here is we're getting a negative fraction. I get at negative 100, negative 5/200ths. At negative 1,000, this dominating fraction is going to be negative 5/2000ths. So it's negative, but because the denominator is getting larger and larger and larger, this fraction is also approaching 0. So even though it's negative, approaching 0 from the negative side, it's still approaching 0. So whether x is positive or negative, whether x is approaching infinity or minus infinity, the function values are approaching 0. and that means y equals 0 is a horizontal asymptote, or the x-axis. Now the last situation. Let's look at an example where the degree of the numerator is greater than the degree of the denominator. And so 2x cubed plus x squared plus 1 over 5x squared plus x minus 3. So again, notice the degree of p is greater than degree of q. So the rule tells us that f has no horizontal asymptote. So let's look at y again here. And so we'll plug in some values. When I compute f of 100, again, these lead terms are going to dominate. And what's this ratio? It looks like 200 over 5, right? And again, the contribution of the remaining terms, they're there, but they're relatively insignificant, right? If we plug in x equals 1,000, yes, I am now saying that 1 million is relatively insignificant, but that's when compared to these other quantities over here, when we have this, what is this, 2 billion amount leading that term. So the dominating ratio here is going to be now 2,000 over 5. And what I want you to see is, in this case, what's happening is this dominating fraction is getting larger and larger. At 10,000, I'm not sure I can even read these numbers anymore. I just wrote it out for you to contemplate. Okay, now I just got to say this. Yes, I am saying that 100 million is relatively insignificant up there in that numerator. And so this dominating ratio is going to be, I think, 20,000 over 5. So in this case, what's a little bit different from the previous one is this fraction keeps growing larger and larger and larger and larger as x gets larger. So as x approaches infinity, f of x approaches infinity. It gets larger and larger. There is no horizontal asymptote. And the situation when x is negative, kind of similar, but there's a little twist here, and I just want to make this observation, that with this function, when I plug in negative values of x, this dominating ratio, notice we get negative 200 over, now they're negative for this function, negative 1,000, the dominating ratio is going to be negative 2,000 over 5. But the difference between this and the previous example is that because they're growing in a negative way, so becoming larger and larger as a negative quantity, that means that we're actually approaching negative infinity, becoming the function values, the y values on the graph are becoming more and more negative. So just in this situation, we actually have something very different happening as x approaches minus infinity from what was happening when x approaches infinity. In one direction, we're blowing up. In the other direction, we're plunging down to negative infinity. Sometimes these are the same. Sometimes these are different. They don't have to be the same here. So that's my explanation. Hope that wasn't too long. Really, what we got to know is our rule, and I want to just put that back up on the screen at the end. There we go. So we can finish with this view, and we're going to apply this rule in some problems now.